Okay, let's dive into something that trips up pretty much everyone at some point, even seasoned programmers. It's a tiny little math problem that actually reveals a giant truth about how computers see the world.
I mean, it seems like the most basic math imaginable, right? But if you type this into a lot of programming languages, you get an answer that's, well, it's just a little bit off. And this isn't a bug. It's actually a deliberate design choice. The reason why uncovers this fundamental conflict in how computers have to handle any number that isn't a simple whole number.
So here's how we're going to solve this puzzle. First, we'll dig into the computer's core problem with decimal numbers. Then, we're going to meet our two contenders for the job. One is built for pure speed, the other for perfect accuracy. We'll see them go head-to-head, and then figure out how to choose the right one for the job.
At its heart, this is really a translation problem. We humans, we think in decimal, base 10. But computers, they live and breathe in a world of binary, or base 2. And just like when you translate a beautiful poem, sometimes something important gets lost in that translation. Think about it like this. In our everyday decimal system, a simple fraction like 1/3 turns into 0.333, just going on forever. Well, in binary, the same exact thing happens to a number as simple as 1/10. It becomes this infinite repeating sequence of ones and zeros. And since the computer's memory isn't infinite, it has to just chop that sequence off at some point. And that introduces a tiny microscopic error right from the get-go.
All right, so how do computers usually deal with this? Well, let's meet our first contender. This is the one you'll find almost everywhere by default. The incredibly fast, but sometimes a little bit reckless, floating point number. This thing is the absolute workhorse of modern computing. There's a standard for it, IEEE 754, which was created way back in 1985 to basically bring order to the chaos of different systems all handling these numbers in their own weird, incompatible ways. You can think of it like scientific notation but for binary numbers. It's designed to be super efficient, and it's baked right into the computer's hardware.
So here's the crucial point. Floating point numbers are sprinters. They are built for speed, period. They can represent this massive range of numbers, from the incredibly tiny to the astronomically huge, all inside a nice fixed amount of space. But what's the trade-off? Well, they sacrifice perfect mathematical accuracy to get that amazing performance.
But what if you absolutely cannot tolerate any errors? What if good enough is just not good enough? Well, for that, we need our second contender, the perfectly precise rational number type. So instead of trying to approximate a number with a decimal that gets cut off, this method takes a totally different, more mathematical approach. It stores the number exactly as it is, a simple fraction. 1/3 isn't stored as some version of 0.333. It's literally stored as 1/3. Perfect. This approach is like a meticulous mathematician. It guarantees perfect accuracy and consistency every single time, which is amazing. But all that precision comes at a cost. The calculations are way slower because they're all handled in software, not hardware, and the memory you need can just balloon as the numbers in the fraction get bigger and bigger. Okay, so let's put these two head to head. Let's see this trade-off in action with our original little mystery.
To us, this is just 1/10. It's simple, it's clean, it's finite, you write it down, and you're done.
But we know now that to a computer, it's this infinitely repeating binary fraction. So when you have to squeeze that infinite number into a finite amount of memory, what value does the computer actually end up storing?
The computer stores the absolute closest number it can possibly represent with its fixed 64 bits of memory. And that number? It's not exactly 0.1. It's this tiny, almost invisible difference that then adds up and causes 0.1 plus 0.2 to not quite equal 0.3.
But here is where it gets really wild. If we take that slightly off number, the computer's version of 0.1, and we ask a rational number type, hey, what fraction does this actually represent? The answer is just shocking.
Yeah, that is the real fraction hiding behind what the computer calls 0.1. It's this enormous, complex ratio. A rational type, on the other hand, would have just cleanly stored 1/10 right from the very start.
And this complexity is the root of that performance gap. Rational math isn't just a simple add or multiply. It needs all these extra steps in software, like constantly simplifying fractions, turning 2/4 into 1/2, but with these massive numbers. All of that takes extra time and processing power.
So, if the sprinter isn't always accurate and the mathematician isn't always fast, how in the world do you choose? Well, it all just depends on what you're trying to build.
It's a classic engineering trade-off. For your bank account, for any financial transaction, you need absolute perfection. Errors are just not an option. But for a video game that's rendering a 3D world, raw speed is everything. A microscopic error in where a pixel is, the human eye will never, ever see it. So the approximation is totally fine.
And this isn't just some theory. Check this out. In this example, you have the same equation solved using floating point numbers with different levels of precision. And look, you get slightly different answers. But when you solve it with rational numbers, you get one single, provably correct answer. Now for something like cryptography or a scientific proof, that difference is absolutely everything.
Ultimately, the floating point system we use every single day is an engineering marvel. It's designed to be tough, to be robust, and to give good enough answers for most of us, most of the time, without us needing to be experts in numerical analysis. It's built to handle a little bit of our ignorance gracefully.
So the next time your computer gives you a funny-looking number, you'll know exactly why. It's the hidden story of the sprinter versus the mathematician. And it really makes you wonder, doesn't it? Where else in our digital lives are we unknowingly relying on an approximation, where good enough has become the invisible hidden default?